Hi, welcome. So, in this video, I want to do some exercises on how to calculate mass defect. So I'll just call this 10B. Or calculating using mass access to calculate the so-called binding energy. Okay, calculating binding energy practically. Okay, so I will use a combination of these lecture notes here, plus some of the Vim. I'm going to use Vim with the types to do it. Okay, so just bear with me. This one will have math in it. If you're not interested, you can skip it, but I'm going to use it. I'm going to make this video anyway, and I want to really introduce you to how to do it using the wallet cards. Okay, this is something I was taught in class quite a while back. Using nuclear wallet cards to calculate binding energy. And this is the foundation of how you calculate the energy from reactions as well. But I'll try not to do concepts here. Let's just focus on the binding energy. Now, how do you find these nuclear wallet cards? Okay, let me close this. Okay, so go to Google Scholar and you'll go here. Click on Google Scholar and you'll find nuclear wallet cards. Okay, I have this from the drop down. What you want to look for is the one from Brookhaven National Lab or BNL. This one's 2004. Okay, it's not the one. You should look for the ones with like 1,000+ citations. This is from 1995 J.K. Tooley nuclear wallet cards. Okay, click on this. You'll get open up to a new PDF. And this is where you will get your nuclear wallet cards. Okay, this is one October 2011. This one's by Brookhaven National Lab. So this is a very important resource. Okay. J.K. Tooley, I'm probably not pronouncing the name right. Okay, but you have a lot of information. What you generally want to do is just keep scrolling until you hit this. This is the wallet cards themselves. All right, so just some things I want to add on, like, okay, let's just zoom in on the ones we are interested in. Okay, okay, we have this number here called the Z. Okay, Z is the number of protons. Okay, Z is the number of protons. This EL here stands for the element. So let's say 1 proton, it means it's a hydrogen. 2 proton means it's a helium, no matter how many neutrons there are. A here represents the total number of nucleons, which is the protons plus neutrons together. Both of them are nucleons. Okay, so number of nucleons in the nucleus. So for example, hydrogen 3, this is called tritium, will have 1 proton and 3 nucleons. 3 nucleons means it has the total number of protons and neutrons is 3. So that's 1 proton and 2 neutrons. Okay, this J-pi here is I think spin parity thing. It's something to do with quantum physics, but you do not have to deal with it now. Okay, this is one of the numbers that should be conserved most of the time. Okay, in beta decay there are some rules that there are forbidden decays that can happen. Okay, but forget it. It's too much information. Just focus on the Z, L, and A. Unless you are really interested in this thing called J-pi, then that's another topic for another video. I'm not doing it here. Okay, this delta here is what we were discussing last time, mass excess. So this is the how do you put it? The energy, or rather the mass of the atom or the particle in comparison to the number of nucleons it has, or rather the number of nucleons times 1/12 the mass of the carbon atom at ground state. Okay, that's a bit of a mouthful. Just 1/12 the mass of the carbon atom, or the carbon nucleus. Yeah, carbon atom. Yeah, carbon atom. Yeah. So that's what we have there. Okay. Let's see here. This is all in MeV. Okay, that makes it MeV is a unit of energy rather than mass. But if you realize Einstein's E equals mc squared, mass energy equivalence, the mass energy equivalence states that you can just convert mass to energy using the factor of c squared, which is the speed of light squared. Okay, so that's this that's what you're seeing here. All the numbers here are in MeV. MeV is a unit of energy. It's about I believe here, okay, 1 MeV equals 1.602 times 10 to the minus 13 joules. Okay, joules. If you're not sure what they are and you're not technical, don't worry. Don't worry about the numbers. Okay, let's just calculate everything in MeV, and we'll just use MeV as our standard unit. Okay, this is the mega electron volt, we call it. Next column here is T half. T half is a half-life. So half-life. So I have not explained explicitly what half-life is just yet, but it is an inverse measure of how fast it decay a nucleus or a particular nucleus is decaying. So the longer the half-life, the slower it decays. Basically, that's that. Gamma, don't worry about it. It's another I think it's a width of something, a resonance width, or I can't remember. Okay, at this moment. And then it says here abundance. Okay, so for example, for naturally occurring elements in hydrogen, 99.9885% is hydrogen 1. Okay, naturally occurring hydrogen. But 0.0115% exists as deuterium. So in nature, if you are just to take out water from the environment, there is a little bit of deuterium inside. How much deuterium? This much. Okay, so this much percent of the hydrogen atoms you scoop out will be deuterium if you take it out in nature. The rest of it is half-life. For example, helium-3 doesn't exist in nature, but it has a half-life. Or hydrogen-3, tritium, it doesn't have a natural abundance, but it has a half-life of 12.32 years. Okay, so that's usually what the pieces of information you will need. This is the last column is decay mode. That means if it's radioactive, how does it decay? And as mentioned in previous videos, neutrons undergo beta minus decay. Tritium likewise undergoes beta minus decay. However, you can see the half-life is a bit different. Neutrons have a half-life about 10 minutes-ish. Tritium has a half-life of 12.32 years. Okay, so because when neutrons go into the nucleus, they're a bit more stable in general. Yeah, actually deuterium, if you bind a neutron to a proton in a deuterium, it doesn't really decay at all. It doesn't decay at all. So yeah. Right, so as far as these wallet cards are concerned, that's what you need. You see these ends here, these actually decay by neutron emission. So for example, hydrogen 4 decays by neutron emission. So it will just emit neutrons. Now, some of these have beta minus and a neutron. For example, here, you have a certain percentage sign. You have a certain percentage sign here. So let's go to one common example in cesium. Okay, it's one of the most famous radionuclides because it's what people are concerned about in Fukushima and so on. So cesium, I mean, I'll just use the find and let's go for cesium. Yeah, cesium is number 55. Right, and what we are most worried about is this bugger right here, cesium 137. Okay, so it says here it's a half-life of 30.8. It decays through beta minus decay. Okay, this cesium will decay into barium 137. Okay, barium 137, or specifically barium 137M. Okay, so partly barium 137N and partly direct into barium 137. Okay. Okay, maybe that was a bad example, my bad. Okay, but anyway, what is this 98.4%? What is this 1.6%? Okay, these are what we call branching ratios. So those are for special cases where there's more than one mode of decay. Okay, more than one mode of decay. So let's just take an easier example. I'm going to see cesium what? Cesium 144. Okay, there's a beta minus and a beta minus n. Okay, beta minus n is what we call it emits a beta particle first, and which is an electron. Okay, beta minus is an electron. Then it emits another neutron. So that's what a beta minus n is. So it says that 3.03% means 3% of the time you will have this beta minus neutron occurring. The remaining time it will just be a normal beta minus. Okay. Now there are lots of symbols here. There are lots of symbols here as to what this beta minus epsilon means. You can actually bring it to the front. Go to the front. Excuse me. Go to the front and you'll see this one. So you see beta minus here is beta minus decay. Epsilon here is electron capture or electron capture plus beta plus. So they don't differentiate between electron capture and beta plus, though there is a important difference here, physics wise anyway, or beta plus decay. Okay, so here is usually beta plus decay or electron capture. That's what this epsilon means. Isomeric conversion, isomeric transition through gammas or conversion electron decay. I believe it's just gamma decay, I believe. Okay, NP alpha, neutron proton alpha decay. SF, spontaneous fission. Some particles do that. I will not talk about it yet. Okay, here we talk about beta minus n. It says delayed neutron proton alpha following a beta minus decay. So this is quite common, as you saw in just now. And this is actually quite important for reactor physics. But we'll talk about that later. Now, let's get straight to the point. How do we calculate a mass excess, okay, or mass defect, or rather binding energy? Okay, so let's say we have here one example of a binding energy, and we'll use the wallet cards, and we are going to use this mass excess to help us. All right, so let's once again, for simple example, use lithium 7. Okay, lithium 7 here. So lithium 7, you see the mass excess here is 14.907 MeV. So let's just write that down. Just give you one example. Lithium 7. So the mass excess is what called delta MeV. Okay, equals how much? Is equals to 14.907 MeV. 14.907 MeV. Okay, okay, what if you want to calculate the binding energy? You want to calculate binding energy of lithium 7. So we have to sort of compare it again. Remember our definitions. Binding energy is the energy release when combining the neutrons, individual neutrons and protons. Individual neutrons and protons into the nuclei or nucleus. Okay, then what is mass excess? Mass excess is the mass of the particle here. Okay. Mass excess equals to mass of particle minus, well, the number of nucleons. That's the easiest way, okay? Number of nucleons. Okay. Minus the number of nucleons times 1/12 the mass of the carbon-12. All right. So what is the mass excess of lithium-7 in MeV? Okay, that is equals to 14.907 MeV. All right. So how is that going to help us? Right? We are going to use the mass excess of lithium and we are going to compare that with the protons and neutrons. Okay. So I'm going to write down the equation like that. Mass binding energy of lithium-7 equals, okay, mass of lithium-7 minus mass of 3p minus mass of 4 neutrons. Okay, we will not find these masses explicitly mentioned in these wallet cards, but we are going to make use of them. Okay, we have mass excess. Okay, mass excess is the mass of the particle minus the number of nucleons times 1/12 the carbon, right? So we can actually substitute that here. Mass of lithium-7 minus 7 times 1/12 carbon-12. And you'll see that a lot of these things cancel out, okay? So I'm substituting mass excess. Okay, so mass of 3 times the mass of proton minus 1 times the 1/12 the mass of carbon-12. Okay, and then last one is 4 times mass of neutrons minus 1/12 mass of carbon-12. Okay, what you will notice if you do the math, you bring this 1/12 the carbon-12 out. This is what we call 1 Dalton. Okay, this is the alternative name for it, or what I mentioned in the last video, 1 AMU. This is 1/12 the carbon-12. If you actually do the math right, okay, this, and this will all cancel out. Okay, this, and this will all cancel out. Okay, so I'm going to do it for you to prove that it's the same. So I'm going to have I'm going to have minus 7 times 1/12 carbon-12 mass. Okay, minus times minus is a plus, so it's a plus 3 times 3 times 1/12 mass of carbon-12 plus 4, because there's a minus and minus sign. 1/12 the mass of carbon-12. Okay, so all of these cancel out nicely. Then you will get your mass. You have your after everything cancels out, you will still have the binding energy there. Okay, plus binding energy of Li7, lithium-7. So binding energy again, it's the mass of lithium-7. Binding energy for lithium-7 is the mass of lithium-7 minus 3 times the mass of the proton minus 3 times the mass of the neutron. 4 times the mass of the neutron. Now what is in these brackets here is the mass excess. Okay, this is the mass excess. Okay, in this case what we have is the MeV. So let me just do some substitution here. So the binding energy of lithium can be calculated using mass excess MeV for lithium minus 3 times the mass excess in MeV of the proton minus 4 times mass excess of the neutron. Okay, so that is how you will calculate your binding energy. So what's this here? 14.907 MeV minus 3 times what is the mass excess of the proton? Mass excess of proton is just the hydrogen mass excess, 7.289 MeV. 7.289 MeV. Okay, minus the mass excess of the neutron. Mass excess of neutron is 8.071 MeV. Just notice here that the neutron is slightly heavier than the proton. That's something you should know offhand, or rather, I'm just telling you now. But if you are going to do nuclear engineering, this is a very important fact you must know. Okay, 8.071 MeV. Okay, so I'm going to use LibreOffice Calc to do this. Of course, I can use types as well. So I want to do it the free and open source way. Okay, so mass of lithium 7. I'm not going to be too particular about the caps and everything. 14.907. So this is MeV. Okay, mass excess. Let's open this up. Mass excess of proton or hydrogen 7.289. 7.289 MeV. Always important to put units. Mass excess of neutrons. Shucks, I have my numlock not configured correctly. 8.071 MeV. So binding energy of lithium 7 equals to this 14.907 minus 3 times mass excess of H minus 4 times mass excess of N. Okay. So yeah, you're comparing the difference between the what do you call the mass you're comparing the difference between the how do I put it? Yeah, you're comparing the mass difference between the lithium 7 and the protons and neutrons. Now, binding energy should not be negative. You have to supply energy to break apart lithium 7 into its constituent protons and neutrons. So should not be negative. Okay, so I think I got my signs mixed up, but the most important is to know that they are the difference. Okay, so this is the correct one. So I kind of I mix up my plus and minuses here, but for me, it's more intuitive to have the picture that I need to supply energy to break apart a nucleus. That's why it has to be positive. Okay, most of the time binding energy, if not all the time, binding energy is positive. Okay, binding energy is positive. You need to supply energy to break apart a nucleus. That's always the rule of thumb. Okay, so this binding energy of lithium 7 is this much, 39.244 MeV. Now let's just also calculate binding energy per nucleon of lithium 7, because that's what you will find on that graph thingy you have. So this is binding energy, 39.2 divided by 7, 5.606. Now let's check whether this is done correctly. I'm going to go back to my physics LibreOffice LibreTexts. And let's go back to that binding energy curve. Okay, binding energy curve, and we'll find lithium 7 right here, 5.606. Okay, this is lithium 7, 5.606. Is it correctly done? Yeah, 5.606 MeV. Okay, so that's how you do your calculation of binding energy per nucleon and binding energy using the wallet cards. Okay, so anyway, I'll put the answer here. Okay, just now was minus 39.2 MeV. I'm not going to bother about significant figures and all that, but I mean, in real exams and real times, you should. The number of significant figures or decimal place, you should follow the 3 decimal places. Okay, because you're doing addition and subtraction, 3 decimal places will do 5.339. Okay, never mind. Let me just do the decimal place. In practice, just conserve as much decimal places as you can, but know that your accuracy and precision is limited by the data you have. In this case, all of them are in 3 decimal place. Okay, so this is how you do it. Of course, note binding energy is positive because you must supply energy to break apart the nucleus. Okay, you must supply energy to break apart the nucleus. So of course the calculations are not useless. You just take away the minus sign, and there you go. Lithium 7 binding energy is this much. Binding energy per nucleon equals 39.244 over 7, and that will give you 5.606 MeV. And that is correct when we take a look at the curve here. Okay, 5.606. All right, so of course I'm going to upload this to GitHub as usual, and I want to especially put a citation there. So I'm going to save the citation. Oh, I'm going to save this citation. Okay, nuclear wallet cards. Okay, I'm going to save this, and I'm going to save it. Of course, you can end the video now if you don't want. I'm just going to put this I'm going to put this here into this text file. Tmarks this nuclear physics, or rather nuclear physics.typ, and I'm going to open up the bit file as well. Doesn't matter. Okay, this Thule nuclear is like that. Split it apart. I'm going to change. Okay. Binding energy can be calculated using nuclear wallet cards. Okay, I'm going to put Thule 1995 nuclear there. Gonna type swatch nuclear physics.type, and let's ocular that. Okay, I do it correctly, and of course you don't need to use Vim or anything to do this. Yeah, I'm just leaving for you the description. Okay, now these nuclear wallet cards are here. JK Thule and others, nuclear wallet cards, Brookhaven National Laboratory. I'll put a citation here so you can go and find it in your own time. Okay, so yeah, I think that's all for this video. Thanks for watching us. See you guys again. Bye bye.